Welcome back to Dr. Liu's VCE Chemistry channel. Today, we'll break down the fuel and heat of combustion questions from the 2024 NHT Chemistry exam. My explanations might need refinement, so I welcome corrections or feedback from teachers, parents, or students. Calorimeters are specifically designed to measure the enthalpy change of a reaction. It's important to remember that only the calorimeter itself has a calibration factor, not the chemical reactions occurring within it. The test tube's cooling indicated an endothermic reaction, and in all chemical reactions, mass is conserved. The pressure of 3.0 moles of a gas in a 60 L container at 127 degrees Celsius can be calculated using the universal gas equation. First, write the combustion equation and determine the mole ratio of ethanol to carbon dioxide. Next, calculate the moles of ethanol, followed by the moles of carbon dioxide. Finally, calculate the mass of carbon dioxide, ensuring the result is reported with two significant figures. Consider a gas sample starting at 10.0 L, 25 degrees Celsius, and 2.0 atm. As the temperature rises to 50 degrees Celsius, while pressure and the amount of gas remain constant, the volume of the system becomes directly proportional to its temperature. This proportionality allows us to calculate the new volume at 50 degrees Celsius. To calculate the calibration factor, you multiply the voltage, current, and time together, then divide that result by the change in temperature. In this diagram, the horizontal axis represents reaction progress, not time. The energy profile diagram itself is unaffected by the quantity of reactants or products, only by their molecular energies, as shown in the chemical equation. However, the average chemical energy of a reaction mixture does depend on the initial quantities of reactants. Since a bomb calorimeter cannot determine activation energy, it can only establish the relative energy positions of reactants and products. We investigated the relationship between an alcohol's structure and its molar heat of combustion using ethanol, propan-1-ol, and butan-1-ol. For each alcohol, we recorded the initial mass of the spirit burner containing the alcohol and the initial temperature of 100 milliliters of deionized water. The alcohol was then burned to heat the water, with the water's temperature recorded every 30 seconds. Once the water temperature rose by 15 degrees Celsius, the flame was put out. We noted the highest water temperature reached after stirring until it began to cool, and then recorded the final mass of the cooled spirit burner and alcohol. Since we aim to determine how an alcohol's structure affects its molar heat of combustion, the type or structure of the alcohol is the independent variable. The key difference among the three alcohols used in this experiment is their number of carbon atoms. Therefore, the molar heat of combustion could be influenced by the length of the fuel's carbon backbone, the number of carbons present, or changes in the fuel's molar mass. We'll determine the heat of combustion of butan-1-ol by assuming that all the energy released is absorbed by water. First, we'll calculate the energy absorbed by the water, which represents the heat released by the butan-1-ol. The mass of butan-1-ol burned is found by taking the difference between the burner's initial and final mass. With these values, we can then calculate the heat of combustion of butan-1-ol. The combustion of butan-1-ol in air can result in the formation of carbon monoxide gas. The correct procedure for balancing a chemical equation involves addressing carbon first, then hydrogen, and finally oxygen. As no specific reaction conditions are provided, water may be represented as either a liquid or a gas. Hemoglobin binds much more strongly with carbon monoxide than with oxygen. As a result, carbon monoxide starves the body's cells of oxygen, leading to carbon monoxide poisoning. To minimize the risk of inhaling carbon monoxide, you should conduct an experiment in a well-ventilated area, ideally within a fume hood, and always follow valid safety precautions. Heat loss from the system is a primary source of experimental error. Other potential errors include incomplete combustion of the fuel, water evaporation, and any heat absorption by the equipment itself, other than the water. Experimental errors reduce accuracy. Specific errors and their effects on the calculated heat of combustion include: incomplete fuel combustion produces less heat, resulting in a lower calculated value. Water evaporation leads to a larger apparent temperature increase in the remaining water, yielding a higher calculated value. Heat absorption by equipment reduces the observed temperature change in the water, leading to a lower calculated value. The results, presented as a histogram, clearly show that the molar heat of combustion increases from ethanol to butane-1-ol. This trend aligns with the increasing carbon chain length from ethanol to butane-1-ol. These findings suggest that a longer carbon chain, a larger molar mass, or more carbon atoms in a fuel all correlate with a higher molar heat of combustion. Research suggests that biofuel production may give rise to several undesirable effects. Potential drawbacks include changes to land use patterns that may increase greenhouse gas emissions. Evaluate the benefits of using biofuels instead of fossil fuels in terms of greenhouse gas emissions. Our model for evaluating biofuel benefits incorporates a flexible structure, allowing for 3 pro-arguments, 1 counter-argument, and an evaluation statement, 2 pro-arguments, 2 counter-arguments, and an evaluation statement, or 1 pro-argument, 3 counter-arguments, and an evaluation statement. This 5-point framework is designed for a 5-mark assessment. Regarding carbon emissions, the use of fossil fuels leads to a net increase in atmospheric carbon dioxide. In contrast, the use of biofuels typically results in no significant net increase in atmospheric carbon dioxide. However, potential drawbacks include the release of carbon dioxide from clearing land for biofuel production, which may reduce overall carbon uptake compared to existing forests. Additionally, the manufacturing and transportation processes involved in biofuel production can release extra carbon dioxide into the atmosphere. Despite these challenges, biofuels are generally considered more environmentally friendly than fossil fuels. Biodiesel can be blended and used in many different concentrations. The most common are B5, up to 5% biodiesel, and B20, 6% to 20% biodiesel. B100, pure biodiesel, is typically used as a blend stock to produce lower percentage blends, and is rarely used as a transportation fuel. Use the chemical structure of biodiesel and diesel to discuss why B100 is rarely used as a transportation fuel. Petrodiesel is a hydrocarbon, whereas biofuels are esters. When compared to petrodiesel, biodiesel has a lower heat of combustion because it's already partially oxidized. This necessitates carrying more fuel to match the petrodiesel's performance. Biodiesel's ester group also results in a higher viscosity, potentially limiting its use due to reduced flow rates. Its lower cloud point is another drawback, as it can solidify in cold weather, preventing fuel flow. Additionally, biodiesel's higher flash point can make engine ignition more challenging. Consequently, B100, pure biodiesel, is seldom used as a transportation fuel. This section, worth 30 marks, 25% of the total, assesses understanding of fuel and heat of combustion. It comprises 7 multiple-choice questions, 7 marks, and 2 short-answer questions, 23 marks. Calorimetry, measuring enthalpy changes, noting the calorimeter's calibration factor. Reaction types, distinguishing endothermic and exothermic processes, gas laws. Ideal gas law problems for pressure, volume, and temperature. Combustion reactions. Examples like ethanol combustion and CO2 mass calculations. Experimental methods. Designing experiments to study the alcohol structural heat of combustion. Energy profile diagrams. Interpreting these as reaction progress indicators. Fuel comparison. Evaluating biofuels versus fossil fuels, especially regarding greenhouse gas emissions. Biodiesel. Its structure and reasons for limited pure, B100, use e.g., lower heat of combustion, higher viscosity, safety and accuracy. Addressing experimental errors and precautions, e.g., ventilation for CO inhalation. Should you require assistance, please feel free to connect via WeChat or WhatsApp and send an email. Thank you for your attention. Kindly note the details of Dr. Liu's VCE Physics, Chemistry, and Biology channels.